This is Toufic, and he's going to talk about the anomaly detection analytics for the data center. So, over to you, Toufic.
Thank you. I am Mike. Hi, thanks for having me here. Just a quick intro about. Oh, it's louder this way, so I'll have to talk like this. So a quick intro just about myself. My name is Toufic Boubez. I'm a founder, CTO of a company in Vancouver called Metaphor Software. Before that, I was a founder and CTO of a company that some of you might know, Layer 7 Technologies, also in Vancouver, who was recently acquired by CA. But I escaped. So I love the CA guys. Thank you. Sorry, they're great people. Go to their booth. I wanted to do something else. That's why I started Metaphor. Before that, actually, I was also founder and CTO of a company called Saffron Technology, which did hardcore analytics for various purposes. And I was a chief architect at IBM before that. So I started the service-oriented architecture team at IBM. So I've been doing this for quite some time. I know I don't look my age, but I've been doing it for a long time. I've been doing large-scale systems for over 20 years. I'm here to talk to you guys about some interesting stuff that I consider interesting. Now, the reason people ask me, well, why do you want to give this talk? And there's some historical background just quickly about the talk, is that in April, back in Austin, at DevOpsDays Austin, I proposed an open, which will happen here today, open space talks. I encourage everybody to participate. They're even, it's hard to believe, but they're even more useful than my talk. So go and participate into the open space talk. But anyway, I proposed a talk about analytics, sort of next generation analytics. What are we doing with all the metrics, with the flood of data metrics that we're bombarded with? And it was very well received, very well attended. And they asked me to write a blog about sort of the results, which I did. You can go and take a look at it at some point. And then I was honored because they asked me again in June in Silicon Valley DevOps Days to take the results and actually give a talk about sort of the 5 lessons learned that came out from that experience. And so I did. But during that talk in June, there was lots of topics that, because of the time, I only have an hour and a half, right? So because of the short time span, I don't really have a lot of time to expand a lot of the topics. So I ended up saying, well, I need like a sequel, in essence, to talk about some of the things that we didn't get to talk about in June. And that's the purpose of this talk. So just a couple of notes. The data is all real. There's no fake data. It's either from my servers or from servers from some of my users. So, I'm not, just so you know. The other thing is that you'll notice most of the data doesn't have labels on the axes, and that's on purpose because it doesn't matter to me. Metrics are metrics. Could be, I don't know, CPU usage, could be memory, could be number of unicorns per second. It doesn't really matter. It's just data, and the information in the data, that's what's important. The other thing is that I have a tendency to talk very, very fast, so I need to remind myself to slow down, and if I go over, some of you guys need to go, slow down, which is fine with me. And I'm supposed to mention the cats because everybody loves cats. So even if you don't get anything out of the talk, you should like the talk because it's got cats in it. So I like to start with the wall of charts. There's something we see all the time. We're used to. We sit down in our monitors. They're everywhere. And we look at data, a mind-numbing series of data. And we ask ourselves, OK, so what does it mean? Like, is this significant? Is this, can I point? It doesn't matter. Well, this dip here is significant. And then we drown in that data. The other reason I like to put up that chart up front is because it allows me to put up Disaster Girl. And it's actually just a side story. There was a challenge back in Silicon Valley about whether you can weave in Disaster Girl into your talk. And I did. And she refuses to leave now. So she's probably end up in all of my talks. But anyway, so we sit and stare at the data and we go, what does it mean? Does it mean anything? What can we do with it? How can we get information out of the data? Useful, actionable information out of the data as opposed to just being data. So the side effects of the wall of charts are twofold. One of them is we get alert overload, which means that, after the 5th time we're woken up in the middle of the night because our servers are surfing that limit between 89% and 91%. And every time they cross over that 90% line, I get, you know, my PagerDuty bill goes up, right? So that we get a lot of alerts, and I love this quote from John, which is alert fatigue is the single biggest problem we have right now. We need to be more intelligent about our alerts, right? The other side effect is that metrics overload. We start looking at all these metrics, and some people, you know, collect tens of thousands of metrics, if not more, and at some point they lose their meaning, right? So we need to be able to do something with all that data, right? And so what we really need is better alerting. So, you know, the question that I always ask myself, well, so what if my, whatever, unicorns per second is surfing that edge between 88%, like I said, and 91%, and every time it crosses over, I get an alert, you know? Who the heck cares, right? It doesn't really matter. What I would much rather know is that it's been at 60% for a while, and all of a sudden it's been starting to rise, you know, for the last couple of hours. That's a lot more significant, a lot more interesting to me than, you know, than the other techniques. But unfortunately, the systems we have today with static thresholds and rules don't help you, right? They're not set up to look at that kind of stuff. So what we need is more intelligent anomaly detection mechanism to be able to deal with those kind of things. And these are the kind of things, this is sort of the new movement in the last year or 2 years or so. A lot of people are starting to look at that, and there's a lot of people who are working on that kind of concept to sort of move the current monitoring tools into the next generation, in a sense. So just for definition purposes, so anomaly detection, you know, is also known as outlier detection, is a search for items or events which do not conform to an expected pattern. I love this definition from these guys. You know, I didn't come up with it myself, but it makes sense. But for us in the DevOps space, what it really means is that what we want to be able to know, we need to know when one or more of our metrics is going wonky. TM, you know. I'll use that word a lot. Right? So we need to know when stuff is going wonky so we can actually do something about it before, you know, what I like to say, the waste material hits the rotary cooling device, right? Because I can't say bad words here. So, you know, we need to know that stuff before bad things happen. So then, you know, but unfortunately, what you've all seen, if you're DevOps, you've all seen monitoring sucks, right? Who hasn't? Okay, good. Whew. I was going to like come up with some punishment, but okay, good. You guys passed. Okay? So everyone's seen monitoring sucks, but it really should be, I love monitoring because, you know, this is what it really should be. Monitoring is awesome if done properly, right? So, so proper monitoring tools should give us all the information we need to be proactive because we spend our time being reactive, right? We're putting out fires, waking up in the middle of the night for PagerDuty, right? That's not the right way. We should be all proactive, but they don't. Because current monitoring tools assume that the underlying systems that we built are relatively static, well understood systems. So because they're static, we can put thresholds and say, all right, if it goes up over this threshold or under the threshold, alert me, and that's about it. You know, so they're good for detecting catastrophic events, like I said, when stuff hits the fan, right? But not much else. The question is why? Why is that? We need to understand why is that the case so that we can actually do something about it, right? So it's because, really, traditional analytics or statistics come from manufacturing process and quality control. So when I'm stamping out cylinders all the time, all day long on a machine, right, I kind of understand that process, and it doesn't change that much. The underlying mechanism or properties of the process don't change that much, right, over time. I've studied it, I understood it, it doesn't change. So I can say things, you know, like, well, if cylinder height goes above a certain level or under a certain level, you know, let me know, alert, and then stop the manufacturing, and then remove that cylinder because it doesn't fit the specs, right? That's where a lot of analytics and statistics, as a matter of fact, in our current monitoring tools, that's where they come from, right? But so, like I said, so traditional analytics is really based on Gaussian distributions. So they make assumptions about the probability distributions of the underlying process. The assumption mainly that is a normally distributed Gaussian distribution. And so it usually assumes that normal distributed and it has a useful and meaningful mean and standard deviation and so on, right? So that's a lot of talk and say, you know, blah, 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 like it means standard deviation, all that kind of stuff. But what does it actually mean, pardon the pun, in our field, in our domain, right? So I look at some metrics here and I'm going, okay, well, you know, what does it mean? There's not much, there's a lot of data, but not a lot of information. And unfortunately, most of our time is spent staring at data versus looking at information, right? And so the question is, well, I have all these metrics that I'm collecting. What does it mean? What's the actual data that's inside of them? Can I do something with them? So then let's pick one. I'll pick one of them and say, all right, what is it, so we'll look at the distribution, right? What is the distribution, the probability distribution of that particular metric? And then, so with a simple transformation, so this is where we go from, data with no information. A very, very simple trick. Just let's run a histogram on that data. And all of a sudden, information comes out of that data. Really meaningful and useful and powerful information. And that information is that, look at that, that all those values actually, they look random up there. Maybe they might be random, but they actually are very, very well behaved. They fit a really nice bell curve, which is a Gaussian distribution. So that means something to me. That tells me a lot of information about the underlying process, so I can actually do something meaningful and useful with it, as opposed to just staring at this, which really means nothing to me, right? So that's sort of what we're trying to do with the sort of next generation analytics. So now, because of this kind of distribution, I can do some interesting things. I can do something like what's called the 3 sigma rule. The 3 sigma rule comes from a very, very interesting property of Gaussian distributions, these things, which is not shared by other distributions. But if we assume Gaussian, we can say that 68% of the values of all values, no matter what, lie within 1 standard deviation from the mean of that curve. We can also say that 95% approximately of all the values lie within 2 standard deviations. What's really, really important, we can say that 99.73% of all the values will lie within 3 standard deviations. That's the 3 sigma rule. So now I can do something like, what? If I put this 3 standard deviations from the mean, anything outside of those 2 lines, I would consider it to be an outlier, because it's outside of the 99.73 percentile of all the values, no matter what, right? So now that's something useful that I can use. And that explains those mysterious red lines that I saw earlier. So now, because this process is Gaussian in nature, which is well understood, which is, in general, what we call it normal, I can put these lines. I can say, well, anything beyond the 3 sigmas, actually, I consider to be abnormal, an anomaly, and I can actually get rid of it or do something about it. So that's really, really powerful, and that's where all these monitoring systems come from. Not only that, but I can do a lot more interesting things with Gaussian distributions. I can do things like moving averages. The big idea here is that if I can look at past values, and from past values, I can sort of make an educated guess about what the next value is going to be, right? And then if I measure the actual value versus what I'm guessing, what I'm predicting the next value to be, and there's significant difference between the two, I can say, you know what, this is not normal, this is some kind of anomaly. That's the general idea. Now, in order to do predictions, people have tried a lot of different things. And because of the nature of Gaussian distributions, you can do things like a simple moving average. So I can take the average of the last, say, n values that I've been collecting in my metrics, and that should give me an idea of where the approximate neighborhood of what the next value should be in the prediction. So I predict that, and then I say, well, once that new value comes in, if it's significantly different from what I expect it to be, then I'm going to send an alert. This is something that's not very, very normal, right? So that's sort of the big idea of a simple moving average. So, but each value in the window contributes equally to the prediction. So even past values that are maybe 2 hours ago have the same equal contribution to what an expected value is going to be. So people said, all right, that's not very, very good, because sometimes, as the system makes changes, new values are more powerful predictors of past values, right? So then people came up with the concept of a weighted moving average. So it's similar to a simple moving average, but now I can look at past values and give them less of a weight than new values. So if I look at a linear or arithmetically declining weights for every value in the window, so older values contribute less to the prediction of the new value. So now it's starting to get a little bit better, but the problem was that neither a simple nor a weighted average deal well with periodicity. What if you have periodicity in your data? Your data moves up and down, let's say, for example, based on time of day or day of the week and so on, right? None of these kind of predictive weighted averages work well. So then people came up with the next level, what we call exponential smoothing. So exponential smoothing is similar again. So we're taking one step higher, which is it's a weighted average type of predictive mechanism. But now instead of linear decreasing weights, we're actually over a limited window. We're actually doing an exponentially decaying weights over the whole past of my sample space, right? So that actually, so again, just the equation here is pretty simple if you're doing actually numerical analysis. So the problem was that is that as bad as moving averages in dealing with periodicity and strength here. So finally, we came to the concept of double exponential smoothing. And this is what everybody, you go onto the forums and you go online and you check stuff and you hear Holt-Winters, Holt-Winters, Holt-Winters. Everybody's doing Holt-Winters for one reason or another. And Holt-Winters really is a, who has heard maybe of Holt-Winters? Okay, good. That's right. So for everybody else who hasn't heard of Holt-Winters, it's sort of one of the most, taunted and touted predictive and anomaly detection techniques today that people are starting to use. So Holt-Winters really is about, is a weighted moving average for predicting values, except that it has two parameters. One of them that deals with smoothing the data, which is what all weighted averages do. And the other one has a factor for dealing with periodicity. So now all of a sudden we can actually account for some kind of periodicity in the data so we can take care of it. So we can make better prediction. So I've spent a lot of time talking about how great these things are. But one thing that I should mention, and you should keep it back in your mind, so we're circling back, is that all these things assume a Gaussian distribution of your data. Right? So Gaussian distribution are very, very powerful because of the nature of these distributions that any time, far, far away in the galaxy, far, far away, far in the future or any time, I can make the same predictions about the data because the statistical properties of the data don't change. No matter how many samples or how long you sample the data, you can sample the data for years. The histogram of that data is not going to change. So you can actually make some powerful decisions and use some powerful techniques to deal with that, like 3 sigma or Holt-Winters and things like that. You can actually, the other interesting thing is you can compare metrics. Even though they're completely different, you can look for, say, cohesiveness, or you look at different kinds of metrics because the underlying characteristic of these metrics are very, very similar. Any Gaussian can be spread or scaled, whatever, to look like any other Gaussian, so you can actually compare them apples to apples. So that's very, very powerful. I don't have music, so this is where it's supposed to be dum, ta dum, dum, But, that's all well and good. The problem is, most of the data that we get in our data centers is not Gaussian, right? I'm sorry for the letdown. I should leave now. Okay, thank you very much. Now, so let's look at real data. So this is actually data from one of our servers. And so again, it's data, it's not information. Again, it's very, very simple to, and again, by the way, just as an aside, there's so many really simple transformations you can use to get data, to get information out of data. And most people don't do that because they just look at, the wall of charts, which is really a bad idea. Anyway, so I look at it, and then lo and behold, it's not a Gaussian, it happens to be a log normal distribution. There's lots of different distributions. But because it's not Gaussian, everything, I'm screwed. So, nothing, there's nothing that I can do. Like the mean, standard deviation don't really mean much. Again, that word again, but really don't mean much. So then all the stuff all the powerful stuff that people download and use, and there's plenty of open source tools and what have you that let you do 3 sigma and Holt-Winters and all that kind of stuff. Now, you should be very careful about stuff because stuff doesn't work most data. Most data that comes from interconnected processes is not going to be Gaussian. So when you've got, response time, there's network delays, there's server delays, there's memory, there's databases, there's your web server, then there's I don't know how many hops to get back to you. All those interconnected processes lead you to non-Gaussian data, right? Gaussian data is generally for relatively more simple processes, right? But most of the stuff that we have to deal with is unfortunately non-Gaussian. Another interesting distribution that you get a lot of time is when you have a mixture of Gaussians. You know, when you have multiple processes, each one of them is Gaussian by its nature, but when you put them end to end, the result ends up being non-Gaussian. This is bimodal because it has two modes, but it could be multimodal data. Again, there's not much that you can do using the traditional, you know, techniques. So then, let's take a look at actual real example data. Again, this is raw data from, actually this is one of our users. I can't say who, but anyway, you can see the periodicity data like based on time of day and so on. But this is actual real data. So then, before I rush in and use any of the 3 sigma or whatever tools, I say, well, let me take a look at that distribution. And lo and behold, it has nothing to do with Gaussian. It's not Gaussian, as you should expect if you've been looking at these kind of things. So then, I tried running 3 sigma rule, kind of anomaly detection on it. And then I get woken up, I don't know how many times every night. That's not good. Right? Well, I could turn off my pager, but then, you know, that kind of defeats the purpose. So I said, aha, I'm not, you know, I'm not going to fall for that. I'm going to use something a lot more sophisticated that accounts for periodicity. So I'm going to use Holt Winters, right? A little bit better, right? I will get woken up a little, you know, less times, but still not so good, right? So this is the danger that just not understanding the underlying characteristic of data can give you. And this is the kind of stuff that you should be thinking about when you're looking at your metrics, right? So the question is about, are we doomed then? There's nothing. Well, actually, we're not. There's tons of stuff that you can do. There's a lot that you can do with data other than just looking at it and putting thresholds. You can do adaptive mixture of Gaussians. You can do non-parametric techniques. Actually, I talk about that in one of my blogs. You can do spectral analysis. Tons of stuff that you can do. And again, just so I can talk about this at the next DevOps. I don't have time to talk about it now. But so just one quick example. So I took that data and actually did a mixture of Gaussian. All of a sudden, the data is accounted for much, much better. And when you run that kind of model, adaptive mixture of Gaussian model on that data, all of a sudden, you can predict a lot better what an anomaly is, what an outlier is. So I can say, for example, these things here should be an outlier or whatever. And then I get woken up a lot less during the night, right? So that's the kind of stuff that you should be looking at. So we're not doomed, but it's really, really important to know your data. You need to understand the statistical properties of your data, where it comes from, so that you can determine what kind of analytics to use. And just keep in mind that a large amount of data in data centers is non-Gaussian. So Gaussian statistics won't work, so use appropriate techniques. Now that I have my soapbox here, my platform, and a little bit of time, I want to go through a pet peeve of mine, right, before they kick me out. Okay, so the analytics talk is over. So pet peeve of mine is that, you know, how much data do we actually need? I've seen over and over and over, every week or every couple of weeks, somebody comes and say, all right, we're collecting data now to the second. Now data to the half second, right? And the question is like, why? You know, what are you going to do with all that data? Is it meaningful to connect that much? I'm not saying it's not, but you got to understand, is it meaningful? So it reminds me a little bit of, I don't know if any of you know Borges. You know, you should get his book Labyrinth. It's an awesome, awesome book of short stories. But anyway, one of the stories about Funes de Memorias. So this guy gives a story about this guy who has perfect recollection. Every detail, every color of every leaf he's ever seen in his life, anything like that. He's got tons of data, perfect recollection of everything about it, but, you know, of every instant of his life, but he has lost the ability of abstraction because he's got so much detail, he can't abstract things out. And that's really, really important, actually, because our brain works on abstraction. We notice patterns because we can abstract, not because we have, you know, information down. I mean, if your brain kept all the information that it's flooded with every millisecond of the day, you would go crazy, right? You can't. So our brain throws away a lot of information. That's why we're so good at detecting patterns, right? That's an important concept to keep in mind when you're collecting data down to the millisecond, right? Is it really that important? But on the other hand, you know, there's a danger to over-abstracting. And I love this because one of my stats professors at one university always uses this example. So you know, says, you know, to a statistician, if you've got 1 foot on fire and 1 foot in ice, on the average, if you abstract it out, you're comfortable, right? You know, so there is a danger to over-abstracting. But you have to be careful about, how much abstraction do you need, but also how much data are you collecting. Do you really need all that data to collect, down to the microsecond, right? So the question, how much data do you need? Well, really, if you think about it, there's all kinds of math and theorems about this. So you don't really need more resolution than twice the highest frequency that you're interested in. That's, the Nyquist-Shannon sampling theorem, right? So, and most of the algorithm analytics will smooth out that data anyway. If you use Holt-Winters or any of those algorithms, they will smooth out the data. And smoothing out means throwing away a lot of the data. So again, you're spending a lot of time, money, storage, and effort on collecting data down to that level, and it's not going to be meaningful to you. So just be very aware of that kind of stuff. The other thing that is related to that is watch for correlated metrics. So for example, use memory versus available memory. If one of them is 100% minus the other, do you really need to collect both? Right? I mean, just think about that. There's a lot of data that is very, very, very strictly correlated, and you're collecting both of them, and you got to think about what. And then you're using both in your analytics. And the question is that skewing your analytics or not? Right? So this is kind of consideration. One of my pet peeves around data. The other thing I did want to bring up, because it's really, really important, and actually the fundamental question in analytics today that is still ongoing, and it's there's two camps in our field, in the data science field. There's the camp of data in data. Data is data. It doesn't matter. Let's collect as much as we can and then analyze everything and analyze and figure out what it actually means. And then there's another camp that says, well, not all data is important, so let's figure out what's important and then understand that and build a model out of that, and then so that we can actually don't waste resources on the rest. And actually, if you want really interesting, smart, intellectual, and fascinating reading, there's like a public bun fight between Google and Dr. Chomsky, who's one of my idols, and Peter Norvig from Google about this whole topic. You can actually go take it there, and you can guess which camp Google falls in. And they're all about building a model. Sorry. Yeah. So that's sort of interesting concept. Keep that in mind. Go read that stuff, and then start thinking about how much data you're collecting, what does it mean, and what kind of analytics you're going to use to deal with your data. That problem, by the way, that issue is unresolved as far as I know. Okay, that's an example. Okay. So I think my time's up. I've only scratched the surface here, unfortunately, but I hope I've given you enough sort of food for thought so you can actually go and start doing your own research and your own analytics and start looking at stuff. I want to talk more about it, but Jenny told me I only allowed half an hour, so I think that's it. And I'm around, so come talk to me during the breaks. Thanks. Do we have time for questions, or? We have time for questions? Damn, I should have talked longer.
Maybe squeeze in two.
Sorry.
Who's the lucky two? You have a mic up there? I think Sean is sprinting down the corridor as we speak. If you listen carefully, you can hear him on the mic. Fancy.
It's not fair. I can't see you.
Has anyone got a question down here so I can pass the mic ahead of time?
Thanks. So in the context of systems monitoring, which is the environment that you're in, certainly there's a lot of value in patterns that are relative to each other.
Yes.
But in many cases, if I've got a gigabit link and my application is outputting, 200 kilobits per second, and then all of a sudden it doubles, oh no, to 400 kilobits per second, I just don't care. It's about the limits. And does your research kind of in algorithms and everything consider how to identify interesting limits?
Okay. So that's... Let me just step back, actually, and I don't. Why would you not care?
Because I'm not going to lose sleep over it at 3 in the morning.
But so, don't you want to know what's causing that? Because what if it goes from 200 to 400, and then tomorrow or like an hour later, it explodes, right? Do you want to know when it explodes, or do you want to know what happens? Like, why did it go in? And
it's a good question. So I might care.
Yeah. Okay. There you go. That's where I wanted it. So you might care, right? So the question is then, if you might care about stuff, there needs to be some kind of tweak. And what I've been looking for, what I've been looking at, and again, there's no real answer yet, but adaptive stuff, right? So, there's two major, again, I wish I had more time to talk about it. There's two major fundamental thoughts of this. One of them is supervised learning and unsupervised learning. So in supervised learning, you build a system that notices that went from 200 to 400, even though it hasn't hit the threshold, but it tells you, hey, something here. And then you tell it, okay, that's not important to me, right? And then it learns over time what's important, what's not important. Now, supervised learning requires the luxury of you sitting down and or training it beforehand. The con of that, so that's the pro. The flip side is that what if the underlying model changes? And then supervised learning is very strict in the model that it learns. It builds a model, right? Unsupervised learning, on the other hand, will adapt to things, but it's a lot harder to do. And right now, the research is still out. We're still working in the community on this kind of adaptive. But we're getting there. There's some really, really good ways to deal with that. But the important thing is that you might care, right? And you need to be able either to tell the system whether you care or not, or let the system figure out on its own over time. Okay?
Awesome, thanks.
Sure.
Hi. The question I have is a little short. When you spoke about all these Gaussian distributions, and if the data is non-Gaussian, can you give us something to, like a name like Holt Winters for non-Gaussian distributions that we can go research on our own?
I did. Mixture of Gaussian. Sorry. Yeah, actually, there's what I would do if I were you. Go look at non-parametric non-parametric techniques, right? Google it. You'll find like there's a wiki page or whatever, and these are the techniques you should be looking at. There's definitely there's tons of them, and not one of them like stands out. There's tons of non-parametric stuff that you can look at. But mixture of Gaussian is sort of one of the first things to think about, because chances are that skewed, strange distribution comes from a combination of multiple Gaussians, right? Just. Hope that answers. Okay.
I've got a follow-up question to what he just asked and what you just answered back. Would you like to come to the R user group and the data science meetup and give a much longer talk just on that topic?
Sure.
I'll answer for him, yes.
Actually,
I'll talk to you later.
Some of the stuff that I was running here just to get some of the stuff, look what I have up. Yeah.
I gotta cut him off.
Okay. All right. Yeah, let's talk about that. Thank you. Okay. Thank you very much.
Thanks, everybody. Toufic will be around. Toufic will be around the rest of the day, so feel free to grab him and ask questions. And Sean Porter's up next. If I can get Sean up here to set up his laptop. And while Sean is doing that, I'm going to grab a couple of our sponsors. They get their 1-minute pitch to tell you anything they like about themselves. So Hootsuite, where is Simon? Okay, come on up for a minute.
Did I hurt you?